Okay. Good morning.
Good morning.
Good morning. I assume everyone can hear me okay.
Yes.
Okay, super. Well, it's a really pleasure to be here. And what I'm going to talk today is a little bit different than what you just heard. I'm going to talk a little bit more broadly on research and implementation of performance-based methods to improve the performance of buildings, but also more broadly to community resilience. I apologize, my examples are not directly related to schools, so I'll introduce my talk with a little bit of background on school safety in California. And I would point out that the work I'll be showing here is really a combination of things by various groups that are indicated there: the Pacific Earthquake Engineering Research Center, another group called the SIM Center, and then a work we do at Stanford as well. California has a long history in school safety, really going back to the 1933 Long Beach earthquake, a magnitude 6.4. This was kind of devastating to that part of California outside Los Angeles, but most particularly 70 schools, unreinforced masonry schools generally, were destroyed, and 120 had major damage. Now, we were lucky in that earthquake occurred at 5:54 p.m. So the schools were mostly empty, but it's been estimated that had children been in schools at that time, there would have been thousands of fatalities in those schools. But nevertheless, this was kind of an important wake-up call about the safety of schools. And it didn't take long for California to quickly enact, actually just a month after that earthquake, something called the Field Act, that really regulates the construction of public school construction with better seismic design standards and with all better quality assurance. And this was important in the Long Beach area, of course, for the reconstruction of the schools that were damaged, but also going forth from 1933, better construction practices. A few years after that, they realized that they should think about retrofit of schools built in other regions before 1933. As you see by the dates there, that really didn't get a lot of action until some 30 years later, 1968, with a deadline to kind of review and retrofit schools built prior to 1933 to complete that work by 1977. Going forward, and I'm just touching on a few of the legislative actions that happened, 1967 to 76 timeframe, there was legislation that required that when schools were designed and built to look more carefully at the seismic hazard, and in particular to avoid construction close to geologic faults. Now, I should point out, over that time too, we had the San Fernando earthquake that pointed out that even though we had avoided unreinforced masonry construction since 1933 for schools, that in fact there were other types of construction, the non-ductile concrete, like we just heard about in the previous talk, that we didn't discover until after the 1971 San Fernando earthquake. So while schools were generally built better over this time, they're still not safe, at least by what we consider by today's standards. 1999, another bill was introduced to require an inventory across all of California to look at potentially at-risk buildings. And these would be ones that were built before 1978, again, looking at the pre-San Fernando type buildings, to take an inventory of those and at least to assess the risk. Nothing required at that point that was mandatory. And in the US, unlike many countries around the world, most of our legislation and laws are enacted locally. So it's really, especially after looking at seismic retrofit programs, many of those, while the state might have incentives, that it's really up to local jurisdictions to develop those programs, raise the funds for those schools. And in fact, a lot of that has been happening in some areas of California. There was a survey based on that 1999 bill looking at schools across California. This just shows that of the big pie chart, a lot of them were wood frame construction, which are actually excluded from this evaluation. They're kind of deemed to be relatively less vulnerable. But in fact, 14% of the schools are considered in the vulnerable. These would not be unreinforced masonry, but typically non-ductile concrete and other types of deficiencies that we've learned and corrected in building codes along the way. More recently, a study in the city of San Francisco looking at schools found of the public schools in San Francisco, about 12% are in that vulnerable category. But interestingly, this study also brought out that about 25% of the students in San Francisco go to private schools, which are not covered by some of these regulations. And in fact, 33%, maybe a larger percentage, given the number of unknown schools, might fall into that vulnerable category. So we still have risks out there. Again, it's kind of local jurisdictions that are really taking the initiative to address these with retrofit. Point out that the Earthquake Engineering Research Institute has a group looking at school safety, and not just in California, but in other states which have not had the same experiences and requirements to avoid unreinforced masonry. And I think the headline of this one is kind of telling, is that now the target is, across broader in the US to have unreinforced masonry, the type of things that were devastating in 1933, rectified by 2033. So, and part of the message here is, well, we have the technologies to do these improvements to schools and to retrofit. Often at times it's the funding and the mandates and the incentives that becomes important to really achieve that. Now I'd like to shift gears and talk about the main topic is performance-based earthquake engineering. And this is basically recognizing that a lot of our seismic requirements are traditionally somewhat empirical. Years ago, we didn't know much about the seismic hazard, so we had a non-scientific definition of the hazard, indirect design approach, and uncertain outcomes. And the whole performance-based method is really to use the best seismology information, direct design approaches using nonlinear analysis methods, and really then looking at having defined outcomes of building performance, not just safety, but damage and recovery time. Now, the way this works, I'll just go highlight some of the details, is, again, looking carefully at each step of the process, starting from how we characterize ground motion intensity, considering local site effects and things of that sort, proximity to earthquake faults, going through nonlinear analyses. You saw some in the previous talk from Taiwan, doing detailed analyses on how the building will respond, but then taking that to the next level to characterize what's going to happen, what's going to be the damage to the building. And finally, the last important point is what's a metric by which we could gauge the performance, not just the safety, but also looking at the damage, what that means in terms of financial loss. And in the context of resilience, what's important is the recovery time for buildings. Now, underlying that kind of logical framework I outlined, there's a lot of mathematics and probability considering the uncertainties, but just recognize that's going on in the background with this methodology. Now, over the last 20 years, or starting 20 years ago, it's been developed, and more recently, this document put out by the Federal Emergency Management Agency kind of codifies or standardizes this performance assessment that I just described. And it's being used now for the design of new buildings and retrofit of existing ones. But a key thing there, again, is that this is describing performance in terms of metrics that can relate to stakeholders and financial programs, insurance programs, and so forth, to try to incentivize better buildings with reduced performance, reduced losses. And again, as we think of resilience, downtime becomes kind of a key metric. I'd just like to illustrate a couple of applications here. One is looking at specific buildings. This is a project that was put on by the California Earthquake Authority to look at existing wood frame buildings, and the Napa earthquake in particular and other earthquakes. We see damage to some of these that in their kind of foundation walls. And this is something that's, when you identify it, it's relatively inexpensive to retrofit, but the question California Earthquake Authority had to quantify what would be the benefits of that retrofit and to incentivize owners to take on those retrofits and maybe to have programs to give grants for retrofits, but also to adjust insurance rates in a favorable way for people who undertook those retrofits. And this is motivated by the fact that we have loss assessment methods. One we use in the US is called HAZIS. And what's shown in this plot here is showing the damage ratio, the percent economic loss to a building, if you would, or to a house based on ground shaking intensity. The blue dots is a lot of the claim data and the damage assessment data from previous earthquakes. And our current methods for these vulnerability functions are statistically based. And as you see here, these curves that are shown in this plot, they go through the data quite well, but they're averaging a lot of scatter in the data from almost total loss to no loss at all and something in between. And the point is, if we want to incentivize retrofit, we have to get better fragility curves that can differentiate the differences between types of construction in houses and whether retrofits have been done to them. So we undertook a study using the performance framework I described, where we did kind of detailed analyses of kind of archetyped or prototype type houses of different 1- and 2-story houses made with different material, wood siding or stucco siding. And we analyzed the structural performance of those, and then we translated it into these damage metrics. And what came out of that, this is just an example of it, is these improved kind of damage functions that can differentiate. In this case, we're looking at what's shown in orange. This would be wood siding houses. What's shown in green would be stucco, sort of a masonry style house. How the vulnerability of them with and without retrofit. So the dashed curves show the benefit of doing a retrofit. And so by quantifying the savings in this way, that can be translated into discounts on insurance, and they could also just incentivize owners to really appreciate the value of the investment in retrofit. And we could take these curves and we could further integrate them with the seismic hazard and look at the expected annual loss or the losses under a certain earthquake intensity. But for this type of house, this relatively inexpensive retrofit can have a very beneficial payback. So this is one example of how this performance framework is used, not just to engineer the retrofit, but also to demonstrate its value and incentivize it. Part of our work now is to take this detailed performance assessment out to a more regional level. I mentioned those kind of HAZUS type methodology that's to look at regional assessment. It tends to use census block, like large inventories of buildings. It also uses these empirical damage functions, but to make that more scientifically based, the performance based, but at a regional level. So that's been some of our recent research, is to develop computational models that can look carefully. In this little puzzle piece is recognizing the fact that each stage of the process, from characterizing the hazard to doing the analyses of buildings to assessing the damage and to look at the recovery, it's complicated parts. And if we could stitch together different pieces of software and different sets of databases and information, that we could allow these computational methods, taking advantage of new information technology and computers, to kind of do these very detailed assessments at multiple levels of fidelity or precision, and looking at trying to characterize the inventory of buildings more carefully. So I'll just kind of highlight some of the things we're doing on different parts of this puzzle. One is on developing the inventory of buildings. We have things like tax records and property sale information is one way to characterize it, but emerging artificial intelligence methods, say image recognition from either satellite or street view images, is one of the ways that we're starting to collect more detailed information on the inventory of buildings in an area. Another is on the damage estimation, is to kind of develop libraries of these damage functions of the types I described previously with the wood frame houses, to basically have higher fidelity models to differentiate the benefits of retrofit, and to, of course, look beyond buildings also to infrastructure and transportation systems. And finally, the goal of this regional thing is to take the detailed assessments that we could do on individual houses, to repeat that over inventories. And in the case of a school system, you could be looking at not just the performance of a school building, but of the school system over a city, to characterize the performance of all those and what's the cumulative effect on the educational system. And what's shown in this plot here is this so-called recovery curve, where after an event, one of the important metrics is what's the time it takes, the cumulative time, to recover the functionality in the buildings that have been damaged. So we've been applying these methods to some case studies. This is one that's shown here for looking at the San Francisco Bay Area under a magnitude 7 earthquake. And I think these sort of scenario studies are important. I started out the talk by saying that the Long Beach earthquake and other earthquakes, certainly in Mexico in 1985, are point out some of the deficiencies in our communities, but if we do these scenario studies before the fact, a hypothetical earthquake, it can point out those vulnerabilities before the earthquake, so we act ahead of time. So this is one where we applied some of these methodologies to do very detailed simulations. As you see in this case, 1.84 million buildings in the Bay Area, and running these on high performance supercomputers. And what I wanted to focus on here a little bit is what's the benefit of these very high resolution simulations. This is the one that's shown in the left view on this slide, versus the more traditional methods that we have for loss assessments, say HAZUS. And one of the differences is the resolution, whereas HAZUS on the right looks at buildings at kind of a census block level, like a neighborhood level, what's the average buildings in the area. The simulations we're doing now is looking building by building for every single parcel. And you could zoom in and look more carefully at that, and then start to ask the question, well, if I could do these very high resolution type of models, what then can I do with that information? And rather than just making a loss assessment for what might happen in an earthquake, what's going to be the dollar losses, what's could be the casualties and demands on medical system, but more importantly, we could look at specific buildings and neighborhoods. We could look at sets of functionality, school systems, or it could be medical complexes and so forth, to look specifically at those and to start to engineer solutions, not just building by building, but on a city level, and to engineer policies. So one example of that is a study that we worked on with the city of San Francisco, looking at tall buildings in the downtown city, a very dense collection of tall buildings built over many different years with different types of deficiencies. And coupled this with San Francisco's initiatives, the so-called Resilient City project that they've had. Part of the Resilient City project was to look at all the functionality in the city, and this table on the right will focus on residential, retail, office spaces, and to think about if you have a resilient city after a major earthquake, how quickly you would like to recover those functionalities in order for this to deem the city resilient. But also to recognize that what's the purple diamonds or the blue diamonds, that would be the targets. The X's are showing what the estimates of what the current population of buildings is capable of, so they don't live up to our expectations. And I'd like to focus a little bit on the question of office spaces being open. And again, the target would be to have 50% of the office spaces open 4 months after the earthquake. Part of this project involved doing an inventory of the tall buildings, specifically looking at the structural systems. This histogram, if you will, shows the numbers and the different types of tall buildings that were built over the last 60 years or so. What's notable though is the Northridge earthquake in 1994 pointed out to us some serious deficiencies in steel moment frame buildings, the buildings that we thought were the best performing buildings. And in fact, as you see in this graphic, most of the tall buildings in San Francisco, shown in the green shades, are these steel moment frame buildings, and most were built before 1994, meaning they have these built-in deficiencies that came to light in the 1994 Northridge earthquake. So this was kind of a focus to think about what's the vulnerability of those buildings, not just on the building itself and its occupants, but also on the neighborhood. And a topic we dug into deeper was to look at the question of cordons around a building. That is, if you have a damaged building that's in risk of collapse, say due to aftershocks, you'll have to set up a safety cordon around it. And this, the consequences of this were demonstrated most dramatically about 10 years ago in the Christchurch earthquake. In fact, we just passed the 10-year anniversary on that, where many parts of the downtown were cordoned off for a long amount of time until buildings were either stabilized or demolished and then could be rebuilt. So we wanted to look at that issue of the collection of buildings in the downtown area. And to couple that with this recovery curve, looking at how much office space would be lost due to damage, not just to the tall buildings, but damage in the buildings surrounding those, but how the recovery of the damage and the repairs to those buildings would be impacted by these safety cordons. So again, we applied the performance-based methods. This time we could look at large inventories of buildings, these tall buildings, where we'd look at both the structural performance, the damage, and then we'd look at recovery times, how quick for the building to recover to its functionality, but also whether the building would be damaged enough to trigger a safety cordon around it, and how long it would take to stabilize the building to remove that safety cordon or to repair the building to remove that. So then we took a number of these archetype tall buildings, and for different shaking intensity, we assessed repair times. And of course, there's a lot of variability in these curves depending on the characteristics of the ground motion, whether it has earthquake pulses in it or whether the duration of the motion, and also how the building responds. The different buildings can respond to that. But we want to characterize in a statistical sense for a given amount of shaking, those repair times. And so we took those sort of models, looked at the downtown San Francisco, modeling both the tall buildings, but also the low-rise buildings around it to look at their repair times. And for, again, the tall buildings, we would be picking ones out and thinking of that, that time, would it trigger having a safety cordon? And if we had that building, then we assumed a safety cordon. And one of the variables we looked at was the different size of that cordon. One of the general rules of thumb is that the safety cordon be 1 or 1.5 times the height of the building, which can encompass a very large area and in fact block off streets in a densely populated urban area. So then, doing that assessment of many buildings in the area, we want to look at recovery time. Again, we were focusing on office space recovery. And in addition to the damage and the repair time for buildings, there's a number of other things we call impeding factors. This would be, for example, the time it takes to inspect buildings, the time it takes to, if it's a damaged building, to hire engineers to design repairs and retrofit to the building, the time it takes to hire contractors and to get financing and mobilization and permits for the building. So all of that can add quite a bit to the total repair time. But then we wanted to introduce to that in this study the effective cordon. So if you have a building that's next to a damaged tall building, that the impeding factor may be not the damage to your building, but actually the cordon in the building next door. And we wanted to see how that can affect the recovery of these urban downtowns. And so in the graphics that you see down below, this is a snapshot, a plan view of looking at buildings in various states of recovery. The ones that are shown in green, these are buildings that are open, that are fully functional. The ones in gray, these are ones that are actively being repaired. The ones in blue, these are ones that buildings, they're waiting for the repairs to begin. That is, they're doing the engineering, they're getting permits and so forth. And the shading in orange is buildings whose repair is inhibited by the presence of they're in the shadow of a tall building. And what's interesting is if you look at the times after the earthquake, 4 months after it, many of the buildings in the downtown are damaged and they're being repaired. But then when you look 12 months out, you find that there's clusters of buildings that are still waiting to be repaired or being repaired because they're in these cordon areas. And again, the concern is when you have many tall buildings co-located in a downtown area, this can be a major factor in slowing down the recovery of that city. So we could then, taking these sort of models, we wanted to then look at some statistics by which one can assess the consequences of the damage to the buildings and the repair times combined with these impeding factors and also the effect of these tall building cordons. So this is that recovery curve I described of the recovery of functionality over time. One could look at, one metric might be to look over a 1-year time frame and to say, what's the cumulative number of office space days, if you will, as a percentage of the total office space that's lost over the first year. That might be one metric that one can look at and assess and ask yourself how much of that is, in this case, due to these cordons around the tall buildings, the safety barriers around tall buildings. We also did studies, the same sort of data, but looking at the variability of the data. Another way to look at the results is to look at that metric I mentioned for the city of San Francisco. The resilience target is to have 50% of the offices open within 4 months. So we could look and say, well, based on the damage in the study that we did, that 4 months out, there might be a 35% chance that you could have all of the offices open. So 50% is your target, and you have a 35% chance of achieving that within 4 months. Or if we look 1 year out, we could see it's a higher percentage of 44%. But then to understand how that's impacted by damage to buildings, but also the damage to the tall buildings and safety cordons. What we then did is began to look at how one can change this. So shown in this graphic on the left is those community days lost for this scenario earthquake, like a magnitude 7 earthquake affecting San Francisco. And it's looking at something like 220 community days lost, meaning you're losing about 2/3 of the office space over that first year due to recovery. But then it's to ask the question, how can you change that through various mitigation policies? And there could be many strategies that are shown here. I'm not going to go through all of them. One might be retrofit of the tall buildings to minimize the number of the damage to tall buildings and minimize the cordons. Others could be to have procedures in place to expedite inspection or to expedite engineering. If owners hire engineers ahead of time, to have them on call to quickly do an assessment of the building and to reduce the time it takes to engineer a repair to a building. Just looking at a couple of them, for example, if you have contractors lined up ahead of time to quickly repair buildings, that can reduce the community days lost, though not too effectively. If you look at retrofitting some of the tall buildings to modern code requirements, that can have quite a more dramatic effect. And again, we kind of looked at the various types of policies or plans that the city or individual owners could impose to kind of reduce these recovery times. We could also look at that second metric I described to look at the probability that you can achieve the recovery times for that the city has, that is 50% occupancy, reoccupancy within 3 or 4 months. So the last couple of points I'd like to end with is to think about that with these tools, we can not only assess what's going to happen to a building, but we begin to assess policies, mandatory retrofit policies or other programs to at least assess buildings and be able to quickly repair and recover from those. And to recognize when we put those policies in place today, their effects are not felt for many years. It might take a number of years for buildings to get retrofit, but we could start to use these tools to quantify that into the future. And we could also anticipate urban growth as part of that. That is, as cities are going to grow in the future, as buildings will naturally be replaced and more buildings will be added, how things we could change today in the building codes and other policies can affect that. So going back to this kind of framework I described to put together the different components of the analysis to look at performance and resilience, there's opportunities on the left side here to examine policy interventions, how that can change the inventory of buildings, also to look at urban growth to see how that's going to change things over time. Along the way, as researchers, there's many things we could do to improve our understanding of earthquake hazards and also the response of buildings and the damage of buildings to those. And then on the right side, looking at the recovery to have a better understanding of how cities recover. That's a socioeconomic sort of problem, but also we could start to look at other metrics. One of the topics for today's workshop or conference is to also look at sustainability. We could also look at the environmental, ecological impacts that say earthquake damage to buildings has, but also more broadly, we could use these sort of computational models to track other sustainability metrics. Okay, with that, I'd appreciate everybody's conversation. Hopefully this came through. Apologies, I couldn't give the talk in Spanish. Thank you.